Okay, hello everyone. Am I audible? Good morning to all. Hello student, good morning. Am I audible?
Yes, sir.
Okay, thank you. Thank you. Okay. So let's start the session. In the last lecture, we discussed the two quantifier. One is a universal quantifier and second one the existential quantifier. And as per his rule, we can check a truth value. Okay, where for which case it will be the true means when this is known as a bare exists means existential quantifier, and every xpx that is known as a universal quantifier. So by using the some conditions, we can check that for which case we can say it is a true output, and for which case we can say the false output for the both the case there exists an or every. Okay, means universal quantifier and the existential quantifier. Okay, and after that we had discussed some examples. Okay, in this topic related to the predicate. Okay, and one domain is given that, and based on that we can check it output. Yeah, okay, for which case we can say it is a true output, for which case we can say it is a false output. Okay, and that was the last example, x plus 1 greater than 2x, where domain of discourse, sometimes domain is also known as a domain of discourse, be the set of all integer and then find the truth value of the following. Okay, so d is given that z a set of integer, and there is some predicates are given that answer of p of 0, p of minus 1, there exists px, every x px, negations. Okay, and then after by using the truth table we can predict this answer of the last two. Okay, so that we had discussed in the last lecture, and then after the second one was there x plus 1 is equal to z. Okay, I think that was remaining. So today we'll discuss some more example related to this, and then after the two topic is remaining, there are two small topic is there. One is the definition of free variable. Okay, and second one the bounded free variable, and the last one was the normal form. So today we'll discuss this topic. Okay, and before that there is one two definition that. Okay, one is the universal quantification, and second one the universal generalization result. Okay, that is based on the definition of universal quantifier. Okay, but that is one separate definition are given, that only definition, that no any counter example are given in this syllabus. Okay, so universal quantification and generalization definition. Okay, so what is meaning of universal quantification? Okay, so the statement every x px is a true, then p of a true for any arbitrary element a belongs to D. Okay, the statement the every x px is a true, then p of a is a true for any arbitrary element a belongs to D. Okay, that is obvious result when we say every x px is a true. Okay, when we say every x px is a true, okay, for all value of the domain, if px become a true, then every x px will be the true. Okay, so here one universal general quantification result is given, that definition is given here. The statement every x px is a true, then p of a is a true for any arbitrary element a belongs to D. Okay, this is called a universal quantification definition. Okay, कोई डोमेन की कोई एक वैल्यू के लिए, आर्बिटरी को एक वैल्यू के लिए p of a ट्रू होगा, अगर every x px ट्रू है, then here it is then. Okay, then p of a is a true for any arbitrary element a belongs to a D. Okay, it is simple definition, only definitions will be followed. And its notations form every x px a true if p of a is a true for any a belongs to a D. Okay, and this is called universal quantification result. Okay, universal quantification definition. And then after generalization result, if p of x is a true when we replace x by any arbitrary value a from the D, then universal quantified statement every x px is a true. Okay, अगर p of x true है, then we replace x by any arbitrary element, any arbitrary value from the domain, then universal quantified statement every x px will be the true. Okay, that is called universal generalization result. Okay, यहाँ पे क्या है, every x px true है. ठीक है, and based on that we are checking P of A as a true or not. Okay, every x p as a true, and here based on this result we can say that P of A is a true for any arbitrary element A belongs to D. Okay, and now here it is a reverse thing. अगर P of x true है, ठीक है, P of x is given that true, and then after we replace x by A, okay, any A belongs to D, then based on that we can say that every x px is the true. ठीक है, P of x is given, that is a true form, and now we replace x by A, okay, x by any A belongs to D from the domain, and based on these conditions we'll say that every x px is true. Okay, that is called universal generalization result. Clear? That is a quantification and that is a generalization. Clear? That is given only definition in our syllabus. So what is meaning of universal quantification and what is meaning of generalization? Clear? Here we consider every x px first as a true, and based on that we can say P of A as a true for any arbitrary element A belongs to D. Clear? यहाँ पे every x px true है, and based on that you have to predict P of A is also true. Okay, और यहाँ पे P of x true है, and then after we replace any x, okay, by A, okay, any A belongs to D, we replace x by A, and we can say that the universal quantified statement every x px is a true. Clear? That is the definition. And after that, that is the De Morgan law for quantifiers. Okay, that is a statement, and we can check the De Morgan law for logic theory, means by using proposition, and this form is there, negations P or Q, that is logical equivalent to negations P and negations Q. Okay, and then second one is the negations of P and Q, that is logical equivalent to negations P or negations Q. Okay, that is the De Morgan law for a logic theory, means for logic by using truth table we can check its proof. Okay, and here it is De Morgan law for quantifier. Okay, so how we can define De Morgan law for quantifier? So let P of x be the given predicates. Okay, and D be the given domain of discourse, means it is a domain. Then first statement of De Morgan law for quantifier theory. Okay, that is negations of every x px, negation of every x px, that is logical equivalent to there exists x negation px. Okay, otherwise there exists negation x px. Okay, that you can also write in this form, there exists x negations px. Okay, there exists x negation px, and second one is there negation of there exists px, that is logical equivalent to every x negation px. Okay, you can also write this form as a every x negations px. This is the De Morgan law for quantifier theory. Okay, and we can also prove it by using such rules of predicate every x px and there exists x px. Based on that we can prove it also. Okay, so why these both are equivalent? Okay, means the negations every x px, that is logical equivalent to there exists negation x px. Okay, why these both are equivalent? Okay, we can how to read this statement. Okay, that is read as negations every x px. Okay, negation every x px, that is logical equivalent to there exists x negation px. Okay, there exists x negation px, and second one is there negation there exists x px, that is logical equivalent. Okay, this sign is for logical equivalent, means both are equivalent. Okay, both are same, every x negation px. Okay, and we'll discuss it proof. Okay, how we can prove this by using the quantifier theory in the lab session. Okay, so we'll prove it also by using such a predicate rule. Okay, by using the definition of predicate and quantifier, and we'll discuss this proof. Okay, in this lab session, but here we'll consider only the statement, the negations of every x px, that is logical equivalent to there exists x negation px. Okay, and second one is there negation of there exists x px. Okay, there exists a negation that is equal to every x negation px. Okay, and the first one is there. So it is a De Morgan law for a quantifier theory. Okay, and this is a De Morgan law for a logic theory. Okay, by using truth table we can check it, but here by using the predicate and quantifier rule we can prove this. Okay, and after that that example we had completed, that is second one. Okay, that is derive the truth table of the following statement: P of x y z, where x plus y plus z is equal to is equal to z, and P of x y, x is a capital of y, means we just predicted truth value. Okay, that is example of predicate is given there, find such three number where we can consider here x plus y is equal to z. Okay. And second one is that x is a capital of y. So just consider any x. Okay. Delhi is the capital of India. Okay, so that is one true form. So we can consider Delhi is the capital of India. Okay. Second one, false statement. Rajkot is the capital of India. So it is a false one. Okay. So for this case, you can predict it false answer for any x and any y. You can consider it here. And if it is a true, then it is a true form. Okay, you will get output is a T. And if it is a false, then you will get output as a false. Okay. For example, Delhi is the capital of India. That is a true. And here it is Rajkot is the capital of India. That is a false. Okay. And here it is x plus y is equal to z. So you can consider that three number any. Okay, where you can consider it addition is equal to z. For example, 1 comma 1 comma 2. Okay, x y z as a 1 1 2. So it will be 1 plus 1 is equal to 2. Okay. So 1 1 2, that is a true form. That is a true output of this predicate. And if I consider a 1 2 3, okay, 1 2, let us take 5. So it is a false output of this predicate because we cannot say 1 plus 2 is equal to 5. Okay. So that is a false one. That is a true one. But that is just a simple predicate example. Okay. And then after derive the truth value of every x px, that is the first one and that is the second one. Okay. So every x px key value आपको decide करनी है truth value. So every x px and p of x is given that x greater than x plus 1 and d is equal to here z. So what is the output of every x px? Is it true or false? X greater than x plus 1 is our predicate. Okay, p of x is given that x greater than x plus 1. That is a predicate. Domain is z. That is include minus infinity to plus infinity. Okay, the set of integer. And here p of x is given that x greater than x plus 1. So can we say this p of x is true for every value of the domain? Then we can say that every x px is true. Okay. And if it is a false for a single value of the domain, then every x px will be the false. So here we can consider a 0. Okay, simple 0. That is first value 0 replace to this equation. So it will be 0 greater than 0 plus 1. Okay, and that is 0 greater than 1 and 0 greater than 1. That is a false in mathematics. Okay, so here we can say that this every x px is a not a true for every value. Okay. And here it is counter example is given that the p of 0, that is a false output, and therefore we can say that every x px, okay, is the false. So this is the answer of this one. And second one is one sentence is given that, okay, and domain is given a four word: umbrella, tricycle, tune, and so on. So the word x include minimum two letter A, P, I, O, U. Okay, five letter are given here, and find out the possibility how many words from this domain as include the minimum two letters. Okay, if it is all the word include minimum two letters, then we can say that every x px is true. Okay, if it is not possible every this four word are given in the domain, if it is not true, then we can say that it is a false. Okay, so first umbrella, that is include a two letter E and A. Okay, so for umbrella it is the correct one. For tricycle, okay, it is include only one word. Okay, that is only E. Clear? And here P tune, that is also involve two word, two letter E and O, and this last word is John, it is only O. Okay, so it is not true that for every value of the domain, okay, for every letter of the domain it include two letter from this A, E, I, O, U. Okay, so what is answer of the second one? Every x px is a false. Okay, and why it is a false? Because in the tricycle, okay, it not include the two letter, it include only one letter. Okay, then after John, the last word, that is it also include only one letter. Okay, so that is the one theoretical form example. That is a mathematical form, and here it is the answer we can take. Okay, and then after answer of there exists x px for this one, x plus 1 greater than or equal to 2x. That is a p of x for the first one. D is equal to the natural line is given. Okay, 1 2 3 4 5 and so on, and p of x is given that x plus 1 greater than or equal to 2x. So what is the answer of there exists xpx for the first one? Is it true or false? So condition of there exists xpx is there. Okay, if it is a true, okay, if the p of x is a true for single value of the domain, then we can say that there exists xpx is a true. And if it is a false for all value of the domain, then we can say that there exists xpx is a false. Okay, that is the conditions to verify the true or false for existential quantifier. अगर डोमेन की एक वैल्यू के लिए अगर p ऑफ x ट्रू है, ठीक है, कोई एक ही सिंगल वैल्यू के लिए p ऑफ x अगर ट्रू है, तो आंसर ऑफ देयर एग्जिस्ट x p x विल बी द ट्रू. ओके, अगर कोई भी ऐसी वैल्यू नहीं है डोमेन में जहां पे p ऑफ x ट्रू बन रहा है, मींस इट इज अ फॉल्स दैट, so answer of there exists x p x will be the false. Okay, so here we can consider a 1. Okay, so answer of p of 1, p of 1 will be 1 plus 1 greater than 2 into 1. Okay, just replace 1 to this predicate, so it will be 1 plus 1 greater than 2 into 1, and that is a 2 greater than equal to 2. Clear? So 2 greater than equal to 2, that is equality mentioned in between them. Okay, 2 greater than or equal to. Okay, so therefore it is the correct one. Okay, that is a true form in mathematics. Why it is a true? Because here equality is given, okay, in between this both value. So therefore it is the correct one. And if you consider another word, another value, okay, let us take a 3. So for p of 3, it will become 3 plus 1 greater than equal to 2 into 3, and that will be the 4 greater than equal to 6. That is incorrect. Okay, at p of 3, this form will be incorrect there. But for a 1, we can check this output is a correct one. Okay, and if I remove the equality between this predicate, then it will be the incorrect. Okay, for any value you can consider, it will be the incorrect there. Okay, it will be the false. But now it is equality is given there, so it will be the true. 2 greater than equal to 2, that is the true form, and we just required a single value to say a p of x is a true or not. Okay, so here it is a p of 1, it become a true. So therefore we can say that there exists xpx is a true. Okay, there exists xpx is a true. And then after second one, sentence is given that the word x contain both letter a and I at least one time. Word x, okay, contain both letter a and I at least one time. Okay, so if it is a true for a single word, okay, then we can say that there exists xpx is a true. Clear? And there is no such word are given in this domain where it contain both letter a and I at least one time, then it is a false. So first take the letter lemon. Okay, it not include a, so that is incorrect. Here it is orange, so a is included but I is not included in the second word. Okay, then after third is a tree, so there is no any a and I is here. And then after false, okay, so in this false word, a is given, a is include but I is not include. Okay, so there is no such word are given in the domain where it include it contain both letter a and I at least one time. Okay, so answer of there exists xpx for the second case, it will be the false. Okay, it is the false for the second example. Okay, there is no such word is given in the domain which is include a and I both. Okay, so these are the example of logic and this example of predicate theory. Okay, that is the next one. It is for practice. Okay, you just try it. That's very easy. That uh, just try it by yourself. Okay, p of x, that is x plus 1 is equal to 1. P of x for second, x square plus 1 less than x. Third one is root x is equal to 1. Okay, d is equal to real line is given that, and check the values of their exist xpx. Okay, all our simple mathematical form is given that, and if it is a correct for any value of the domain, okay, then it will be the true, and if it is incorrect for any value for all value of the domain, then it will be the false. Okay, so just practice it by yourself, this okay one, and you just also try it for every xpx for these three functions. Okay, check the answer of every xpx also. X plus 1 is equal to 1, x square plus 1 less than x, and root x means x raised to 1 by 2 is equal to 1. Okay, just check the answer of true or false for there exists xpx as well as every xpx. Okay, both part you have to be here. Just practice it by yourself. It's very easy. Okay, and for any doubt, any query, we'll check in this lab session, otherwise in next lecture. Okay, so next topic of this unit, that is bound and free variable. Okay, so how we can check the bound and free variable for any compound predicate form, okay, predicate statement. So bound and free variable means if a quantifier, okay, if a quantifier is applied on variables x, then the occurrence of the variable is bounded and the variable is called the bounded variable, okay. If the quantifier is applied on the variable x, okay, means for example there exists x px, so here it is x is implement to the px, okay. So what does it mean? This p of x is called the bound variable and so on. This x is known as a bounded variable. So if a quantifier is applied on the variable x, then the occurrence of the variable is bounded and the variable is called the bounded variable. An occurrence of the variable is not bounded by a quantifier is said to be the free variable. Okay. For example, there exists x px conditionally to the qx. Okay. So there is no any occurrence of x to the qx. Okay. We just implement there exists x px. Okay. We just implement this x to the px only, and then after we implement to the qx. Okay. So this qx is the free variable for this case. Okay. So occurrence of the variable is not bounded by a quantifier is said to be the free variable. And here every x and there exists x px. Okay. This form are called the scope of the quantifier. Okay. So first we'll check the bound variable. Then after free variable, and then after we'll check which scope is given in this form. Okay. So bound variable means if the variables the quantifier is applied on the variable x, then occurrence of the variable is bounded. Okay. And if it is the variable is not bounded, then we'll say it is the free variable. And if anyone is included in this statement, every x otherwise there exists, so these are known as a scope. So here there exists x px is a scope. The x are implemented to the px, okay, that will px will be our bounded and the qx will be the free variable. So let us check some example related to this one, and here two counter example are given that we consider the following proposition to determine the bound variable, free variable and scope of the quantifier. Okay, free variable, bound variable and the scope. So one compound statement are given, that compound form is given here. Okay, and just predict a bound variable, free variable and the scope. So here first uh, statement is given that every x p of xy. Okay, every x p of xy. So every x, okay, means x is implement. Okay, so x is the main variable here, and we'll use this value to predict the y there. Okay, that is every x p of xy. So x is the bound variable for this case, y is the free variable. Okay, and every x px, that is our scope. Clear? X will implement to derive the y, okay, by using this p of xy. So x is the main variable here, that is bound, the occurrence of this variable, and therefore we can say x is a bound variable, y is the free variable, and every x px is the scope. Okay, now in second one there exists x p of x conditionally to the q of x. Okay, so there exists x px is only for p of x. Okay, there exists p of x, there exists p of x, so it is only for p of x. Okay, so x is a variable in p of x. Okay, and p of x and q of x, that is x is a variable in p of x and q of x, and so p of x is the bound statement, and it's a bound form, bound variable form, and with the variable x, and which q of x is the free statement. Okay, because there exists is only implement to the p of x. Okay, so for this case this will be our bounded variable. Okay, bounded statement form, which include the x is a variable, and q of x will be the free statement. Okay, because by using this answer we can implement this answer to the q of x. Okay, so first we'll apply x to the p of x. Clear? So for this case p of x will be the bounded statement. Okay, and q of x is the free statement. Clear? And we can say there exists x px. Okay, there exists x px is a scope. Clear for this case? Okay, so it is simple definition that free, bounded and scope of the quantifier, and that type of questions ask for 1 mark only. Okay, we check the bounded variable, check the free variable and check the scope. Okay, so any form or given that if it is include every x p of x form. Okay, as a third example, by conditionally to the q of x. Okay, so here it is also similar, every x px is the scope, then every x px implement to the px first, okay, and then after we'll use this answer to the conditionally qx. So for this, px will be the bounded statement and qx will be the free statement. And here every x px will be the scope, okay, for this type of question, okay. So definition easy, bounded and free variable, okay, and just derive the output, okay, based on this result. Okay, which one will be the bounded variable, bounded statement, otherwise the free variable, and third one is a scope. Clear? And now the last topic of this unit, that is a normal form. And just I write down it because there is one software issue in my laptop. Then some symbol, okay, I could not type by using the math type software, okay. So just I write down it, but when I upload this PPT, okay, I will include this all this handwritten data in this PPT, okay. So let us discuss the normal form. There is first definition is given that, and then after we'll solve some example related to this. So what is meaning of normal form? A better method to transform the expressions p and q to some standard form of the expression as a p dash and q dash, okay, such that a simple comparisons of p dash and q dash show a p logical equivalent to the q, okay, and the standard form are called the normal form, okay. For example, if we have such a expression as a p conditionally q and so on, okay, let us this is one expressions here, p conditionally q, by conditionally q conditionally r, and so on. So that is one expressions here we have as a p and q, okay. It is a p, that is, let us say, q. And now we just convert, okay, we just replace this conditional operator by conditional operator, okay, by such connectives, means by using and operator, by using or operator, we just predict the new form, okay, of this statement, that is the, let us say, q. And that's form, okay, the derived form without using the conditional operator, okay, the derived form by using applying such rules, such law, and so on, will get one form, okay, without include the conditional operator, by conditional operator, and so on, okay. So we'll get one form here, okay, without this operator, okay, after applying such rules, such laws, and so on, okay, we'll get one another form, and this form is known as a normal form, okay, comparison to this one. So method, a better method to transform the expressions p and q to some standard form of the expressions p dash and q dash, such that a simple comparison of p dash and q dash shows whether p are logical equivalent to q. Means you can consider that is a p here, and you will get one its normal form as a q. So this both are equivalent form, okay. You will find one another equivalent form without using the conditional operator in between there, okay. For example, in De Morgan law, what we are doing, we have a p or q, okay, negations of p or q, that is logical equivalent to negations p and a negations q, okay. So this is the logical equivalent form. This is a p here, there is a q here, and both are equivalent. In place of negations p or q, we can use negations p and negations q also, okay. So that is another form of this one. And now in this normal form, what we are doing, we have one of expression is given that which include the conditional operator, by conditional, and so on, okay. And now we'll remove this conditional, by conditional, the operator by using such rules and law, okay, standard law, and we'll get one another form which include the or operator, and operator, negation, and so on. And that is a more better, okay, to solve it, to predict the answer directly. So that is called normal form, and will derive by using such procedure and so on. So for simply city, we use the word product, okay, in place of conjunction. We'll use the product in place of conjunction. That is for normal form only. We'll use the product word in place of conjunction, means in place of and, okay, we'll use the product. For example, if we have here p and q, okay, this form is given here, it is read as a p and q, but in this normal form we say that product of p and q, okay. In normal form we'll say the product of p and q, okay, and means product, okay. And if it is given that or p or q, So we'll say it is a sum of the product. Okay, in this normal form, we'll say it is the sum of the product. Okay, so and means a product. Will replace this conjunction means and operator by the word product, and for or operator for disjunction, we'll use the sum. Okay, so this is read as product of P and Q. Okay, otherwise disjunction of P and Q, conjunction of P and Q, otherwise P and Q. Okay, and this is known as a sum of P and Q, otherwise disjunction of P and Q, otherwise simply say it is a P or Q. Okay, but in this normal form theory, we'll use this word product and the sum in place of conjunction and disjunction respective. Okay, and then after there is a two types of normal form in this topic. First one is the disjunction normal form, that is known as the DNF, and second one is a conjunction normal form, that is called CNF. Okay, two types of normal form is here. One is the disjunction normal form, and second one is a conjunction normal. Okay, so what is meaning of DNF and CNF? Let us discuss. So disjunction normal form, what is that? Okay, in a logical expressions, a product of variable and their negations is called an elementary product. Okay, for example, P and Q. So this is a product of variable. Okay, P and Q are the variable. Okay, similarly negation is also variable. So product of variable and their negation is called elementary product. This is called elementary product. P and Q, P and Q and negations are. Okay, it is a product of P and Q. This is a product of P, Q and negation are. Clear? And operator means a product. Clear? And operator means a product we'll consider in this theory. And or operator means a sum. Clear? And also the sum of variable and their negation. Okay, sum of the variable and the negation is called an elementary sum. Okay, elementary product means product of the variable, and elementary sum means the variable are defined by using the or operator. Okay, means the P or Q, that is a sum of two variable P and Q. Here it is a sum of three variable P, negations Q and R. Okay, that is a sum of the three variable P, negations Q and R. So sum of the variable and the negation is called elementary sum. These are the elementary sum. Okay, and these are the elementary product. Clear? Which include the statement. Okay, the compound form are combined by using and operator. That is the product that is known as the elementary product, and which is include the sum. Okay, which include or operator that is known as the elementary sum. And now after that we'll define the definition of CNF and DNF, means disjunctive normal form and conjunctive normal. So logical expression is called a DNF if it is a sum of elementary product. Okay, if it is a sum of elementary product, means we consider the product or elementary product, and then after we'll combine this bracket. Okay, which include the elementary product. Okay, now check this first bracket and second one. This is the elementary product. By using the AND operator, I include that P and negations Q and R. So these are the elementary product, and now you have to sum it. Okay, so we'll combine this both product by using the OR operator. So this is called sum of elementary product. Okay, again I repeat that. What is meaning of DNF? Okay, we just consider the logical expression as a sum of elementary product. Sum of elementary product. This word is important for us. Sum of elementary product means first we'll identify the elementary product, the include the variable form, which include the product of the variable. Okay, the statement include the product of the variable, and then after you have to combine it by using OR operator. Okay, so this is called a sum of elementary product. Okay, these are the product is given there, and now we consider 1 plus 2. So what is a 1 and 2? 1 and 2 are the elementary product. Okay, two bracket are given that, which is known as the elementary product. Okay, and now you have to sum it. So we not write a plus sign between them. Okay, just use the OR operator between them. So it is called a sum of elementary product. Clear? That is called a DNF. Okay, that is called a DNF. Means such expressions, such logical expressions will convert to this form. Okay, which include the sum of elementary product. That is called the disjunctive normal form. Okay, that is called DNF. And then after second one, CNF. So what is meaning of CNF? A logical expression is called a a conjunctive normal form, that is known as a CNF, if it is the product of elementary sum. It is a product of elementary sum, means check the bracket 1 and 2, okay, in the second definition. So in the bracket 1 and 2, that is a sum of P and R, okay. In the second bracket is a sum of negations Q and R, so it is called elementary sum. 1 and 2 are the elementary sum, and now you have to product it, okay. So that is 1 into 2, that is a product sign, but in place of this cross, we'll use the AND operator, okay. And we know that AND operator is known as a product of the two form. So it is the product of elementary sum, that is called CNF, okay. Sum of elementary product, that is called DNF, and a product of elementary sum, that is called a conjunctive normal form, that is known as the CNF. Clear? And we'll consider this more example after that. That is more example. The first one, P and Q and R, okay. That is the negations are P and Q, negations are bracket over or negations Q and S or P and F, okay. So now check the first bracket, first, second, and third. There is given the product of the variable, okay, product of the element. Clear? And after that, after the bracket, which sign is given? That or operator sign is given there. So what is it meaning of that? It is a sum of elementary product. It is a sum of elementary product. So it is called a DNF. Okay, sum of elementary product. And then after the reverse things, if it is a product of elementary sum, okay, in the second example, P or Q or negations R or S, bracket over and negation Q and S and negation S, okay. So it is combined by using the AND operator. So what does it mean? In the inside bracket, there is all operator are in form or, okay. That is the variable are combined by using or operator. Second bracket is also, okay, it is the or, not and. That is the Q, negations Q and S, or S. Okay, and here it is the and, then after the third bracket, there is only involved negation S. Okay, so it is known as a product of elementary sum. Okay, product of elementary sum. This notation is for the product. Okay, so it is the product of elementary sum. So it is called the conjunctive normal form, that is called a CNF. Okay, then after third one, P or R, okay, bracket over and, then after again the two bracket is given there, this one, okay, Q and P or negation Q. Okay, so it is not in proper form. Okay, proper form means it is not, we can say, sum of elementary product and product of elementary sum. Okay, because it involves the mixed type. Okay, mixed type of operator, that is and, then after Q and P or negations Q. Clear? That is, this bracket is important for us. Okay, it is Q are combined with this bracket also. Clear? So therefore, we cannot say it is one types of normal form. We cannot say it is a DNF. We cannot say it is a CN. But in place of that, if we have this one, okay, I just modify this one as a P or R, then after N, Q, then after bracket and P or negations Q. If it is in this form, okay, just it is the matter of bracket only. Okay, so if it is in this form, then we can say it is the product of elementary sum, and that is called a CN. But now it is a bracket is given that, so therefore we cannot identify it DNF or CN. Okay, so it is not any normal form. Okay, we just convert to the such normal form by using such rules and so on. Okay, and then after the fourth one, negations P or Q or R, that is the DNF. Okay, it is a product of, it is a sum of elementary product. Okay, that is negations P or Q or R, and it is the negations P and Q and R, so it is called the CNF. It is the product of elementary sum. Okay, and it is a sum of elementary product. Okay, that is called DNF, and that is called CNF. Is it clear to all? Condition of CNF and DNF. Is there any doubt to anyone? Okay, is there any query? Okay, so this is a two definition is important for this topic. okay, check the derive the CNF, okay, and the DNF. Okay, so how we can identify, okay, the normal form of any compound statement, okay, which includes a conditional, biconditional, and so on. So procedure form, okay, procedure to find DNF as well as CNF. So first step, okay, remove all conditional operator, tautological implications, biconditional, okay, by an equivalent expressions containing the connectives or operator, and operator, and negation only. Okay, we can use only this three one, okay, to replace this conditional, biconditional, and tautology. Okay, we have such rules and such standard formulas we have in this topic, okay, in this chapter. So we can replace this conditional, biconditional, and this tautological implications by using the or operator, and operator, and the negation. Okay, means it is a sum, product, and the negation. Clear? We have to replace by using this three only. Clear? Or, and negation. Okay. Second, remove the negations before the sum and the product by using the De Morgan law. Okay. For example, De Morgan law we have is, okay, if we have the negations before this bracket, okay, otherwise sum, that is the sum of the P and Q, okay, and it is the this one. So we can remove these negations, okay, before the sum and product by using the De Morgan laws. That can be written as a negations P and negations Q, and that is logically equal to negations P or negations Q. Okay, so by using De Morgan law, we can remove this, okay, this negation. And after third one, apply the distributive law, okay, and now one point is here, the negations should be inside the bracket, not outside the bracket. Okay, negations means we cannot say this is if we consider one more example in this case, so we cannot say this is a DNF, okay, P and Q and negations R, okay, then after V negations Q and S, and then after V P and S, okay, that is not a DNF. Clear? This negation should be inside the bracket, not the outside part. Clear? So how we can convert this negation to the inside? So we can use the De Morgan law, okay. So it is the second rule. Then after third, apply the distributive law until a sum of the elementary product is obtained. Okay, sum of elementary product is obtained. Otherwise, product of elementary sum is obtained. Okay, apply the distributive law there to predict the CNF as well as DN. Okay, so these are the rule. Just we replace this type of connectives. Okay, this type of conditional, biconditional, tautology, and so on by using or, and negation. Okay, and we'll use such well-known rules, okay, to predict this normal form, to derive this normal form. So this is a procedure and this is the conditions to identify the normal form. Okay, सिर्फ आपको क्या डिफाइन करना है, जो भी कंपाउंड स्टेटमेंट दिया गया है, ठीक है, उसमें कुछ कंडीशनल ऑपरेटर होगा, बाई कंडीशनल होगा, ठीक है, उसको रिप्लेस करना है, ठीक है, बाय यूजिंग सच इक्विवेलेंट एक्सप्रेशन and which include or operator and negation only. Okay, and if it is negations before this sum and product, we can remove it by using the De Morgan law. Okay, and apply the distributive law also there until a sum of the elementary product is obtained. Okay, and after that, these are some well-known rules. Okay, that we had already discussed in this theory, in this concept of logical equivalent case, and then after a truth table theory and so on, we can use it to predict such answer. Okay, these are the equivalent form. फर्स्ट वन इज नेगेशन ऑफ नेगेशन पी. अगर कोई ऐसा पॉइंट है टॉपिक में, ठीक है, कि जहाँ पे दो बार नेगेशन है, सो नेगेशन ऑफ नेगेशन पी दैट इज इक्विवेलेंट टू द पी. ओके, दैट इज द फर्स्ट वन. एंड देन आफ्टर सेकंड इज द कम्यूटेटिव लॉ, पी और क्यू दैट इज कम्यूटेटिव टू क्यू और पी, पी एंड क्यू दैट इज कम्यूटेटिव टू द क्यू एंड पी, दैट इज द कम्यूटेटिव रूल. Then after third is the associative law. If it is required this form, you can use it there. Okay, that is the P or Q or R. It is equivalent to P or Q or R. Okay, and then after P and Q and R, that is equivalent to P and Q and R. And this is important. These two are important. Okay, that we'll use in, I think, each and every case, each and every example. Yes, distributive law and the De Morgan law. So distributive law is here. P or Q and R, ठीक है, P or Q and R, that is the sum of the product, okay, P and P or, okay, that is a Q and R. Q and R is the product, so it is the sum of the product that is equivalent to a P or Q and P or R. And what is meaning of that? It is a product of the sum, okay, product of elementary sum. Check this, that is a product P or Q, so that is a sum here, that is also sum, clear, P or Q, that is a sum, and here it is given that product, okay, so it is a product of elementary sum, and here it is given that a sum, and it is a product, okay, so it convert to the vice versa, okay. If it is we have sum of the product, then we can convert to the product of the sum by using the distributive law, okay. And second one is there a P and Q or R, that is equivalent to the P and Q or P and R, okay, P and Q or P and R, that is equivalent to this one, and here it is given that uh that is the sum, okay, P or R, that is also sum, and here is a product, so it is a product of elementary sum, product of elementary sum, that is equivalent to the, here it is the product, it is a sum, and this is a product, so it is equivalent to the a sum of the product, okay, sum of the elementary product, clear. So this will use in each and every example to identify the normal form, and this is a distributive law, and this is a De Morgan law. Negation of P and Q, that is logical equal to negations P or negation Q, okay, the first one, and negations of P or Q, that is logical equivalent to negations P and a negations Q. That is also important to convert to remove the negation, okay, before this bracket, and we can find out this normal form, okay, that is the normal form we can consider, clear. So this is a De Morgan law, and distributive law is important. This first one is also important, negation of negations P, that is a P, and after that we'll also use this result to convert this conditional by conditional, okay. So P conditional Q, that is logical equivalent to negations P or Q, okay. इसका फॉर्म क्या होगा, दैट इज नेगेशंस ऑफ पी और क्यू, दैट इज ऑल्सो इम्पोर्टेंट, ठीक है, पी कंडीशनल क्यू आप दूसरे किस तरह से फाइंड कर सकते हो, यू कैन यूज दिस वन, ओके. If it is difficult to understand P conditionally Q, then in place of that you can find this answer, okay, negations P or negations Q, okay. So this is equivalent form. Otherwise you can use the negations P conditionally negations Q, okay, that is also one equivalent form, negations P conditionally to the negation Q, and you will get the same answer of all these three, okay. If you derive answer of P conditionally Q first, let us say it is a, it is a B, and it is a C, by using truth table you will get the same answer, okay, in these three columns, so they are equivalent. Then after second one, P by conditionally Q, okay, that we already discussed in this that topic, okay. That is equivalent to P conditionally Q and Q conditionally P, okay. The answer of biconditional relation, P conditionally Q and Q conditionally P. Otherwise you can replace P conditionally Q by negations P or Q, ठीक है. P conditionally Q है, so how we can convert to the connectives form, तो P जो है that convert to the negations P, ठीक है, और यहाँ पे conditionally है that will convert to the or, ठीक है, negations P and Q as it is there, negations P or Q, okay. By using that you can convert this one. Then in this example we have to replace this conditional operator, okay, by using such connectives. So जो फर्स्ट वेरिएबल है, ठीक है, उसका नेगेशंस डिफाइन होगा यहाँ पे, कंडीशनल है दैट कन्वर्ट टू द और ऑपरेटर, ठीक है, और सेकंड जो है वो सीरीज रहेगा, ठीक है, नेगेशंस P और Q. If it is given that by conditional, then how we can define, that is a P conditionally Q and a Q conditionally Q, clear. That result will use for the by condition, clear, P conditionally Q and Q conditionally Q, clear. This both are also important, okay, for the derive the normal form, and this rules are also important, okay. And now let us implement to the first example, okay, all this one. Convert to conjunctive normal form means we'll first find the C and F, okay. Conjunctive normal form and define karna. So what is meaning of conjunctive normal form? It is the product of elementary sum, okay. Product of elementary sum means inside जो होगा bracket, that will be the product, will include the uh, that is the or operator, that is the sum. Okay, and after that we'll combine this bracket by using and operator. ओके, दैट इज द प्रोडक्ट ऑफ एलिमेंट्री सम, ये प्रोडक्ट है, ठीक है, और इन दोनों का प्रोडक्ट हो रहा है दोनों ब्रैकेट का, दोनों ब्रैकेट में क्या है, दैट इज इंक्लूड और ऑपरेटर, मींस इट इज अ सम, सो इट इज अ प्रोडक्ट ऑफ एलिमेंट्री सम, ठीक है, प्रोडक्ट ऑफ एलिमेंट्री सम, ठीक है, दैट इज कॉल्ड Cn. So we'll convert this form, okay, we'll convert this form to this one, okay, by using such rules, by using such properties and so on. So compound statement is given that negation of bracket negation P conditional negation Q bracket over and negation R is given that, okay, this form is given. So that is logical equivalent to, first हम क्या करेंगे कि we'll remove this conditional operator, ठीक है, we'll remove this conditional operator. So what is the rule of conditional operator? If we have P conditionally Q, okay, then it is logical equivalent to negations P or Q, okay, it is the negations P or Q, ठीक है, फर्स्ट जो स्टेटमेंट है उसका नेगेशन हो रहा है, देन आफ्टर और एंड देन आफ्टर Q as it is. So here it is a negation P conditional negation Q is given there, negation P conditional negation Q is given there. So it will be equivalent to a negation of negations P, ठीक है, फर्स्ट स्टेटमेंट इसका नेगेशन डिफाइन हुआ अगेन एंड और ईयर, and the second one as it is, second is negation Q as it is there. Okay, so here we just remove the conditional by using the definition, okay, by using the rules. So it is negation of negations P or negation Q, okay, it is the first step, remaining data are as it is there, okay, and then after we can write negation of negations P, okay, that is equal to P negation ka negation, that is equal to the as it is form. So here we'll replace a P, in this case P or negations Q and a negation R, ठीक है, remaining all data as it is there, P or negations Q and negation R, ठीक है, and then after here we apply the De Morgan law. So De Morgan law क्या है, that is equal to a negation of A, let us say use the A, okay, P is इसमें भी P इन्वॉल्व हो रहा है, let us use the A notation. So A or B, okay, negation of A or B, that is logical equivalent to negation A and negation B, okay, that is one form of De Morgan law. You can also consider as a P and Q form, that is similar. So negation of A or B, that is logical equivalent to negation A and B, and here we have and, so we can use this form here in place of or use the and, okay, so it is the second form De Morgan law, negation of A and B, that is logical equivalent to negations A or negations B, correct. So apply this De Morgan law to this form, क्योंकि यहाँ पे negation है outside में, ठीक है, that is negations one, that is our bracket, and that is first bracket, that is a A, and second negations are, that is a B, clear. So it will be a negation of A or a negation B, clear, it is the negation A it is the negations A or a negations B, clear, that is the answer of the De Morgan law, clear. So negations of A means the bracket as it is that, and now यहाँ पे B already negation R है, so 2 times negations will be mapped there, okay, negation of negation R, clear. And then after simplify that, negation of negation R, that will be right R here, okay, so it is the negations of P or negations Q or R, clear. Next step you will get, and after that again apply the De Morgan law to the first bracket, okay, to this bracket, apply the De Morgan law here. So it is the negations of P or Q, okay, negations of P or negations Q. So it logical equivalent to negations, if we have A and B form, then it is A or B, that is negations A and negations B. So it is the negations P and negation of negation Q, okay, that is the 2 times here, or R, that is easy. Negation of negations Q, that will be the Q, clear, negations P and negations Q or R. So this form you can say it is the DNF. Why it is DNF? Because it is the sum of elementary product, okay. If it is here we required answer DNF, then up to this stage you have to solve it, and this answer is called the DNF answer of this form. Okay, but here it is required the CNF, so we apply the distributive law here. Okay, so it is the PQR, so it will be P or R, negations P or R, and Q or R. Okay, so now check this form. It is the product of elementary sum, that is the product, and that is both are involved the or operator in this bracket. So it is a product of elementary sum, so it is called the CNF. Okay, and if it is mentioned here find the DNF answer, then you have to solve up to this stage. This is answer of DNF, and now apply the distributive law. After that it will be the CNF. Is it clear to all? Have you any query, any doubt? We'll discuss some more example, and again we'll discuss this example in the next lecture. Okay, I think 12:40 is already. Just 1 minute, we'll take the attendance and then. क्या समझ में आया?